PV, and that will grow to about 100 megawatts in 2025 to about 150 megawatts in 2037. The rate of growth is changing over time. That's because we think the incentives are going to phase out at some point, probably in the 2022-23 timeframe. That the economics will change going forward. That will affect the rate of adoption of solar PV as well. That's the base forecast, and as I said earlier, we also tested a high solar PV scenario, specifically testing 1,000 megawatt in 2025. The sort of timing of that amount is not critical. It's the 1,000 megawatt that we wanted to test. And in the VELCO study, picked 2025 for that. And if you wanted to reach 1,000 megawatt in 2025, we need a very high growth of solar PV. Say 700 megawatts in 2018 versus 350, so double what we expect this year. We'll continue to grow at a very high rate to get to 1,000. So this is very aggressive. I understand that. Timing may not work that way, but we have tested 1,000 megawatt in the system just to understand whether the system can accommodate that amount of solar PV if there's any issues.
What's the one data point circle? Sorry.
That's 1,000 megawatt.
That is the 1,000.
Yeah. Gotta bring attention to that. Okay, so going into the results, this analysis was done a little differently. Right? We do a peak load analysis. Peak load, we model it at the peak hour for winter and the summer. Here, we're looking at the generation side of the analysis. And we want to find out whether the system is able to accommodate a large amount of generation. And to stress the system, we actually have to model a lower load level. So the analysis here is modeling spring load, the type of load you see in April, May, and a weekend, Saturday or Sunday. So our load is lower, generation is really high, so that the transmission system is being stressed from kind of an export perspective. So we have a lot of generation that needs to flow on the system. So in this case, we have all the renewable generation at maximum capacity. On a spring day, really wet, right? There's like a snow runoff in April. It's very windy, so wind plants are at full capacity. It's starting to get sunny as well. So actually the solar PV is at full output. And this year, our lowest load was on April 23rd. It was not at night. It was in the middle of the afternoon at 2 o'clock. We had about 350 megawatts in Vermont because of the contribution of solar PV. So that's at the time that we think the system will be stressed, will be required to accommodate a lot of generation, not just the solar PV, but hydro generation, wind generation, all at once, because you've got all this renewable fuel that's available, that these resources are going to want to run. Right? And in terms of sort of thermal generation, the biomass units, McNeil Wood or Reigate, landfill are also running at maximum output, but the diesels, the gas turbines are turned off. So all renewables, including the biomass units, are running, and our loads are lower. That's putting a lot of stress on the system. So that's what's being modeled in this analysis. So I have 510 megawatts. That's what we forecast in 2025. And that's turned on top of everything else. And the way we had to do this, and it's, we can forecast the solar PV, but what we find difficult is to actually determine where that solar PV will show up. Where is it going to grow? Is it going to be in the central part of Vermont, northern portion of central Vermont? And the assumption that we used here is essentially said, what if solar PV continued to grow just like in the past, right? So we're using the 2018 solar PV distribution across the state, and we've increased the solar PV at the same rate in all the areas. Right? So this table that you see here shows that the state is divided into 16 zones, all planning zones. Take Newport, for instance. It has a gross load of 19.8 megawatts. This is the load that you would see in Newport without any solar PV. It's just the load that we need to be served there. If we add 14.5 megawatts of solar PV in Newport, then the net load that the transmission system will be called to serve is about 5 megawatts, 5.3 megawatts. So that's how we modeled solar PV across the state. So for the gross load total, it's 618.7 megawatts. And the losses that we measured on our system is 33.6. So that's without any solar PV, right? If we add 510 megawatts in the state distributed in this fashion, the first thing we saw is that our losses went up. Our losses went up by 13 megawatts. And it was kind of a surprise to us when we saw that. And the way we understood what was going on is that in some areas, you see here that some areas there's more generation than the load can absorb. Okay, when that happens, that it's a reversal of flow. Instead of the distribution system serving load from top-down kind of direction, the distribution system is forcing power up on the transmission system. So there's actually increased flow on our transmission lines, and that actually increases losses on the system. It's kind of a little surprise, but it kind of makes sense. We actually increasing flow, not reducing flow. Typically, we think of energy efficiency of solar PV as reducing load. In this case, because there's so much in some areas of the state, we're actually increasing the flow in the system. And the other thing we're also finding is that there's voltage collapse in northern Vermont. It's like a blackout that would happen. In northern Vermont is a constraint today. It's called the Sheffield Highgate Export Area, or SHIA for short, where generation is being curtailed today to avoid this kind of problem. And here what we did is we did not sort of pay attention to that. So let's continue to grow solar PV as it is today, not trying to respect any constraints on the system. And because we did that, we're causing a voltage collapse in northern Vermont. And certain areas of the state, particularly in the northern portion, some of our lines are being overloaded. They're exceeding their capacity from Highgate down to Georgia. And that's even with us trying to reduce imports from New York. Plattsburgh to Sandbar tie flow is at 0 in this case. And we have a device at our Sandbar substation that allows us to push back and flow that wants to come in Vermont. If Vermont in the spring has a lot of renewable energy, northern New York also has a lot of energy, particularly wind. So in April and May, all the wind generation is actually running in New York, and it's being exported out of New York. One of the paths is the Plattsburgh Sandbar that comes from New York into Vermont. That's what the system wants to do, but we have a device that can push that power back to New York. That's how we're modeling the system. And even with that assumption, we are finding problems in Vermont. So that's the results for the base forecast for 500 megawatts of solar PV in Vermont.
When you use the present tense, we are finding problems in Vermont. Are you saying in this scenario?
In the analysis, in this scenario.
And I just wanted to make sure I understand. You said look at where PV has been distributed historically and use that and just grow that model. It does not consider distribution utility hosting capacity.
Right. Right. So this is just transmission capacity alone. We actually cannot model, or the distribution system is not modeled in our software. We don't know what the distribution capacity would be, what the constraints would be in the distribution level.
Hans, can you explain sort of the protocol for operating the Sandbar park in terms of I assume you have to talk to New York about what you're doing with it, whether you're pushing back or sort of pulling in, or
Sure.
just explain how that works.
Right. So the way that the Plattsburgh sandbar tide flow is operated, it's actually it's done at the ISO level. So it's ISO New England, it communicates with ISO New York, determine what the flow needs to be, or what it should be, and the VELCO operator makes it happen. The VELCO operator has its hands on the actually push a button or tweak something to make it happen. But the decision is actually made on the ISO level. It could be made because of a sort of general flow from New York to Vermont. It could be as a result of a constraint, whether it's in New York or Vermont. And it could actually be in New Hampshire, where there's a transformer that we use. We call it a physical regulator. It's like a valve that allows us to change the flow. And ISO New England direct the Vermont electric, VELCO was operated to change the flow. For constraints, New York, Vermont, or New Hampshire, or simply because to sort of accommodate the export that we would see in May, for instance.
So Hans, a question. The interface between New York and New England is in terms of what's flowing, is typically defined on a day-to-day basis on contracts. That is, if New York is selling to New England, and the New York tie, the PV20 tie is one of those ties, right?
Right.
And would they allow us to turn the PV20 to zero if we had a local problem because of this generation?
Yes.
Even if they had contracts to deliver into New England?
Right. So Vermont, the PV20 is one of the 7 ties across the New York, New England interface. There are multiple, actually more than, within Vermont, there are actually 2 ties. The Plattsburgh tie is controlled, the Blissville tie is controlled. So we have the ability to push or pull power on these 2 ties. And when we do that, the contract flow could be the same, it's just that it's rerouted on the other lines. So the 345 lines in Connecticut will carry more power if we push back on our ties. So we can say we don't need that, but it wraps around and it comes through Connecticut to go to Massachusetts, for instance. So we're not stopping flow, we're just stopping flow on our ties. So that's allowed.
And do we have similar ties with Massachusetts and New Hampshire?
We have one tie with New Hampshire that is controlled from their Comerford hydro plant to Williamstown Granite 30 kV substation. We have physical regulators on that tie as well. It allows us to control flow. These are devices that we installed as part of the Northwest Reliability Project. Allows us to optimize the capacity of the system. We can pull power from our neighboring states based on our needs, and we can help our neighbors as well, but you actually can get too much flow. We've found that New York, for instance, wants to push their power into Vermont, and there could be so much power coming in from Plattsburgh that it would overload certain facilities in Vermont. And so the ties allow us to use as much as we can. It allows us to postpone transmission projects. Don't take so much from New York that would actually cause a problem. So it's allows us to optimize the system. It's a really nifty kind of piece of equipment that we've used on 3 of our ties, PV20, the Blissville tie, and the Granite to Comerford tie.
And nothing with Massachusetts?
Nothing with Massachusetts, correct. Maybe there's a need, maybe there's a lot of generation in the southern portion of the state, we may do that. Currently, we do not have a device with Massachusetts.
So it's a similar question. I'm really trying to understand. You're talking about a day like April 23rd as an export scenario, but our neighboring states are also having the same amount of renewable generation. So the export is difficult. Is that? There's
Currently, we don't see that issue. There's export concerns in certain pockets of Vermont, particularly in the northern portion of the state. But once it gets to so we can control that. So we limit generation in that area, but the rest of the state is fine. So we can run as much generation as we can. There's no issues exporting that power to New Hampshire or Massachusetts today. But certainly with 500 megawatts of solar PV or higher, our analysis is indicating that there could be some concerns on the system, even with our ability to control flow. The areas of the state where there's voltage problems or actually exceeding transmission line capacity.
Isn't Deerfield connected to a Massachusetts line of wind? And is there a flow back and forth there between us and Massachusetts?
Yes, right. So Deerfield is connected to a 69 kV line from our Bennington substation down to Harriman and then to Adams. Adams would be the Massachusetts substation. And depending on the relative strengths of the system, power could flow from Vermont to Massachusetts, or it could be the other way. It could be from Massachusetts over to Vermont. Depends on how much wind power is flowing there. This is a little part of the system that's kind of isolated from the rest of the Vermont system. There's quite a bit of wind there and some hydro. There could be some export issues down there, but not to the degree of require curtailments of generation today. So we're going to go into the 1,000 megawatt solar PV scenario. We actually did this 3 different ways. We used the 2018 solar distribution. One way that solar PV would grow in the state. And then we said let's grow it based on the load ratio share, megawatt load ratio share, and also an energy ratio share. Try to see whether if we distributed solar PV differently, whether you'd have a different result. And this is what we found in our analysis. So doubling the solar PV from 500 megawatts to 1,000 is pretty severe. Losses increased quite a bit. Increased from 13 megawatts in the 500 megawatt scenario to about 50 megawatt delta. So very significant increase in losses. There were large flows on the transmission system, overloading a number of lines in Vermont. There were voltage collapse, particularly in the northern portion of the state. We saw low voltage on the bulk system, 115 kV and higher, and high voltage in the substation. So the system are being decoupled a little bit. You have to pay attention to what's happening on the subtransmission level at 35 kV, 46 kV versus the transmission portion of the state, so that the devices that we use to control voltage don't run in the same way. If we switch on a capacitor bank on the transmission system to help the bulk system, it actually can hurt the low voltage or subtransmission system. So that's indicating to us that we might need some dynamic voltage support as opposed to switching in a device, a capacitor bank, which is like could be 25 megabars at a time, like a big chunk of reactive or voltage support. We're going to need a more refined, a finer control of voltage. We call dynamic support, which is a lot more flexible in the system. So we find these issues using the 2018 solar distribution. We also found the same problem, whether it's a megawatt load ratio share or megawatt hour load ratio share. Same voltage problem, same thermal issues. The only difference is that in a megawatt or megawatt hour load ratio share, there were fewer transformers that were affected, fewer transformer overloads, where everything else was about the same. So the changing the distribution of solar PV from 2018 to megawatt hour did not make a big difference. That's what we found. And to explain the constraint that we're seeing today in Shia, our Sheffield Highgate export area, this is an area that's being monitored today and does not have enough transmission capacity to accommodate the amount of generation that's inside the kind of the red circle, that area. And today, generation is curtailed and reduced to avoid transmission concerns. The concerns that we're worried about is voltage and thermal. And what ISO does is it uses a sort of automatic way of directing generation to reduce their output below a certain level every 5 minutes. And we are studying this area. We've actually conducted an analysis back in July, published it, and the report is available on our Vermont System Planning Committee website. Wrote a paper on that. And currently what's happening is there's a study group comprised of the distribution utilities that's trying to select the preferred option to resolve this issue. And this is relevant because the problem that we've been describing the problems look like the Shia problems, right? So the voltage and thermal. Currently, Shia is limited to this northern portion of the state. But if we add solar PV in the same way that we are today, same distribution, our analysis is indicating that there are a number of lines on the western portion of the state, from Highgate down to St. Albans, Georgia, Essex, all the way down to Rutland. These lines would exceed their capacity under contingency or outage events. And there are certain transformers, these locations where you see the circles, actually exceed their capacity as well. So this Shia problem, we could see that expand to other parts of the system. I mean, you have voltage issues and thermal issues all the way down to Rutland. I labeled them sort of Shia 1 to 3 to 5, but there's no sequence as to how this is going to occur. You could have a large generator that connects in Addison County, for instance. So you could jump from Shia to Shia 4 because of the location of the generation addition and how quickly it gets installed on the system. The timing also is unknown, and it depends on how quickly renewable energy is installed, and these kinds of decisions are made by developers, customers, and there's no...
Well, it's these are concerns about additions of new supply. It could be renewable. We're studying renewable here, but what about a large one of the DC projects were to deliver power to, say, New Haven? What would be...
Exactly, right. So, so suppose that the 400 megawatt AVDC project connects in 3 years, and currently it's being, I guess the project is located here at New Haven, right? It's like in Shia number 5, for instance, right? So it's 400 megawatts that gets connected there. When that happens, you can see Shia 5 materialize before Shia 3, and it could happen just like that in 1 year, and that project comes in. And that affects how much solar PV you can accommodate north of New Haven because of that single project that connects on the system. Or you can have a number of smaller projects, but in aggregate, it could be an issue, right? You can have a 50 megawatt wind plant or 20 megawatt solar PV. You have 2, 3, or 4 of them. If they're connecting on wrong location, you can have another boundary. It could be Shia 3, it could be Shia 2, or Shia 4. So this is sort of indicating where constraints could show up depending on where generation is located and how much is actually connected on the system in these areas.
As I understand it, in the existing system, as these new PV systems come online, the constraints are applied to the pre-existing systems that are large enough for ISO to regulate them. Is that a constraint that is inherent, or is that because ISO isn't regulating down to these smaller units? For instance, if the new 500 kW solar knew that when there was a constraint, they were going to be turned back, as opposed to, say, Sheffield or Lowell, would that make a difference?
Right, so the reason, you're right, so the reason why the Sheffield and Lowell being affected, because they are dispatchable by ISO New England, and the smaller resources are behind the meter, they're considered load reducers, they're invisible to ISO, and so then was the concern on the system, ISO can only reach out to the resources that are visible and are being dispatched in the market, right? If the 500 kilowatt resources were dispatchable, then they would also be affected, but only to the extent their economics would dictate, right? If the 500 kilowatt unit was zero price, or maybe it could accept negative prices, maybe they wouldn't be the ones to be curtailed, would be someone that is, or a project that's more costly or more expensive.
But
So it
those
depends.
are all, but those are ISO policies, not technical.
ISO, yes.
Right.
To what extent are the distribution utilities coordinating with VELCO with respect to projects that are proposed that could cause, you know, a jump to SHI 4 or SHI 5 or something like this? Do they involve you when they are looking at the impact of new projects in those areas to see if it's going to affect and expand the transmission constrained area?
Some of the utilities do. Some better than others, and I think I would say that Green Mountain Power, for instance, there's a project with some 500 kilowatts, for instance, wants to connect, or 1 megawatt or 2 megawatt. The planning engineers there would notify us and request that we review these projects to ensure there's no impact or anything that we're concerned about. But I don't necessarily get these calls from all the utilities. I think it could be improved. There's no requirement for the utilities to reach out to us and inform us of where projects are being connected and whether there's an issue that could develop over time.
But it's fair to say that all of the utilities, or most of the utilities, are involved in conversations about SHIA and solutions involving SHIA. So this is something most of the utilities are very much involved with, understanding what the problems are on the grid and in looking at the solutions, including, we were looking at transmission solutions, other groups are looking at non-transmission solutions, electrification, storage, and things like that.
So when we
Is the implication here that based on where PV ultimately gets distributed, that current dispatchable generation could become constrained? So, you know, McNeil could eventually face the do not exceed signals
Sure.
of Georgia Mountain.
Exactly. So currently, Georgia Mountain is not affected. Georgia is essentially in SHIA 2. Today, the constraints are only north of the SHIA line, right? So if we had enough generation in St. Albans or in this part of the system, so much so that we've developed into a SHIA 2 constraint, then that brings in all generators in this area, including Georgia Mountain. If, say, SHIA 4 we develop over time, then McNeil, which is in the Burlington area, would be affected because it is dispatchable by ISO and it would be subject to curtailments.
This is a very difficult place to be, 1,000 megawatts on our system, and that's 50 megawatts of losses. That's probably a peak number, so mean, we could convert that into, otherwise, what's that worth to Vermont? It's millions of dollars on an annual basis.
So that's right. So 50 megawatts at a particular hour, with using the conditions that were tested. 50 megawatts. Hour to hour could be lower, could be higher. So it's a megawatt, not an energy number. It's for 1 hour only. So when we found this issue, we presented that to the VSBC, and there was a discussion around what this analysis was indicating, what it meant for Vermont. We received a lot of good feedback, and we actually came back to the drawing board and did some additional work to try to determine whether there's a way to accommodate 1,000 megawatt of solar PV in the state without causing all these problems. Is there a way to do that? And we performed the analysis. Actually, okay, so quite there. This slide shows a non-transmission alternative to the transmission issues we're finding. Essentially, the location of storage. For instance, at SX 115 kV, we would install 150 megawatts of storage to eliminate problems southward, south of Essex. And then there are a number of subtransmission connected storage to address voltage as well as thermal issues on the local level. So that's our sort of non-transmission alternative to the transmission issues that we're identifying.
And what sort of storage are you projecting for that?
So the type of technology, the lithium ion that we assumed, and the type of cost that we're seeing is about $600 per kilowatt hour. We're thinking that we need about 4 hours of charging at those locations. So that's 150 megawatt device or storage would need 600 megawatt hours of capacity, energy capacity, to resolve the problems that we're finding. Lithium ion, but it doesn't need to be that. We just use lithium ion as one technology to allow us to estimate this, but it could be pump hydro, could be other types of batteries, flow batteries. For the sake of sort of estimating, sort of give you a kind of a reference point, we use the lithium ion technology for this.
How do you arrive at those cost figures in the right-hand columns? What do they represent?
Was based on $600 per kilowatt hour cost. So that's what that's based on. So 600 megawatts versus SX would be 600 megawatts of energy. Multiply that by 0.6. That would yield $360 million for that.
Over 4 hours?
For 4 hours.
And do you compare that somewhere? Is there a comparison to a fix that was this is a non-transmission?
This is non-transmission alternative.
Is there a comparison to a transmission?
Yeah, yes, there's a, I remember correctly, it's page 36 of the plan, as a list of transmission upgrades that would be required. Essentially, we conductor the lines that are highlighted in blue from Highgate down to Rutland, and to replace transformers at those locations here. There's also a number of subtransmission issues that were found. There's a cost associated with that, with all those upgrades. So this non-transmission alternative would be the.
And are those more or less expensive than these non-traditional?
The non-transmission alternative is more costly from a sort of installed cost basis. We did not try to calculate or at least estimate what the market value of those resources are, or that it would participate in the ISO markets, whether it provide regulation, frequency regulation, voltage regulations, or participate in capacity market or energy. This is the sort of the installed cost of storage compared to the installed cost of the transmission alternative. yeah, so this is somewhat simplistic in the way it's shown there. We didn't go into the market aspect of this. There's also other costs that we're not taking into account, like storage is only, could be 5 or it could be 10 or maybe 15 years of life, where you need to replace the storage as the battery dies at some point, right? So there's a refurbishment cost that's not included in here. So maintenance cost is not included in here. So it's comparing the install cost versus install cost.
Would any of these problems be considered something that would be PTF, or is it all considered local to Vermont because it's caused by the installation of new generation in Vermont?
You know, local to Right, so we did another type of analysis to try to resolve these issues by optimizing the distribution of solar PV based on transmission capacity. We did not look at distribution concerns or any types of concerns like that, no land use issues. This is just looking at transmission capacity and optimizing solar PV to avoid issues. There's some assumptions that we use in analysis to, and they're somewhat optimistic, I think. So we're, for instance, we're assuming that all of our AC ties are going to be maintained at 0 megawatts. We may not be able to do that. If the New York system is really strong and there's a lot of power that wants to come into Vermont, we may be able to push against that, but only to maybe 50 megawatts, right? We can't go to 0, perhaps, right? So we're assuming that we're capable of maintaining 0 megawatts to allow more solar PV to be installed within Vermont. We're assuming that the solar PV that's installed is able to provide grid support. It says provide voltage regulation to help in our dynamic voltage issues that we're finding. We're assuming that load is not being reduced by energy efficiency or other matters. Right? If we're reducing load, it's like adding generation. It's actually it's not very beneficial from a generation hosting capacity. And the other assumption we're making is that we're allowing the system to exceed its capacity by 5%. That is to account for potential curtailments. Don't know how much that will be. Maybe a little bit of storage. Some of the solar PV will be installed with storage at the same time. There could be some load management. So we're kind of accounting for that by allowing the system to exceed its capacity by 5%. Today, there's some issues on the subdivision level. We're assuming that those will be resolved going forward. And these types of issues, we're kind of ignoring them as part of this analysis, again, to allow as much solar PV to be installed as possible. We're assuming that the distribution system is capable of addressing any level of storage of solar PV that's connected to the system. We're saying there's no constraint on the distribution level. We're only concerned with transmission. One major assumption, again, is assuming that the larger scale resources will not connect. None of the FERC-regulated resources, the wind plants, the solar PV plants, the large HVAC projects will not connect going forward. Somewhat optimistic. I think some of them will actually connect to the system. Again, that allows more solar PV to be hosted within Vermont. And the distribution of solar PV that works is one that really needs to be followed very closely because the system is interconnected. Remember, we had 16 different zones within Vermont. If we say that one single zone has to have, say, 100 megawatt solar PV for this to work, if that changes, well, it affects other regions that are connected to that zone. So that the individual zones, the values actually matter, as well as the total amount.
Let's put a dramatic pause right there and take a 10-minute break, and we'll see the results of your optimization when we come back.
All right.
Very large problem. There's plenty to do.
Yeah.
Forcing my way into the
Yeah. So you're off the grid?
I'm getting off the grid because I don't want to pay $18 a month for them to be able to use my battery services. I mean, batteries.
Do you have batteries?
Yeah, batteries are what they need, and for
Yeah,
me to have to pay for them is more than I can do. So I'm not being a good citizen.
Right.
I'm not paying that $18 a month to use my free services.
All right, we're back from our break, and we're going to hand things back over to the VELCO team. And Ann, do you have a question?
I think Hans is going to be able to answer it, but the question is if you could give just a little bit of explanation about the 50 megawatts of additional losses that would be experienced. And I'm assuming you're talking about line losses, and if you could just explain a little bit, 2 minutes, what those are, or give a little context for that statement.
Right, so imagine you have a source, the generator on one end, connected to a customer through a line, right? So there's sending power, you're receiving power. Ideally, you'd want every sort of megawatt or energy that is sent through this line is actually absorbed or consumed by the customer. What happens is the connection between the sender and the receiver is called lossy, or it needs certain energy to be consumed in the equipment itself. And the equipment could be a line, a transformer, or any sort of piece of electrical equipment. And the loss is energy that is not consumed by the customer. It could be generated as heat through the air. When current flows through a conductor, it heats up the conductor. It is energy that is thrown out in the air, but it's not being consumed. And we say the energy is lost. So it is something that we want to avoid. We do that by increasing the size of the conductor, a number of things like that. And try to serve power as close as possible to the customer to avoid the transmission from the sender to the receiver. So the 50 megawatt is of losses, lost energy is not good. It's not a reliability issue. It's going to require an upgrade or anything like that. It's just part of the system, how power flows on the system. It's one of the things that happen.
And the reason I noted 50 megawatts, is the city of Burlington's peak is somewhere around 60 megawatts. So you're almost at a Burlington amount of power that you're losing as a result of that particular load study.
Thank you very much.
Just a follow-up. So if those are kind of remote generators, you have, whether it's net metering or standard op or something, they're paid for the actual megawatt hours that they generate, but you're saying there's losses along the way, so that they're not, that the DUs are not then recuperating the customers?
Right, so you have excess generation. There's not enough load that's going to absorb that generation. So it has to flow on the system to actually go elsewhere. And elsewhere it could be within the state, or if you have enough, it could actually go to other states. I mean, it's not, if there's not enough generation load in Vermont, it will go to New Hampshire, it will go to Massachusetts, to where the load is. And you know, that generation that's flowing on our transmission system is increasing our flow and incurring more losses. It's the customer, the end customer is actually further away from that resource. That is what's going on. Okay, so we're at the sort of assumption slide. This is a set of assumptions that are a bit optimistic, and we did that to see how much solar PV can actually be accommodated in the state. So here's the result. result is that we can accommodate more than 1,000 megawatt in Vermont, but only if the solar PV is distributed in this way. And you'll see that out of the 1,000 megawatt solar PV, most of it, a good portion of it is in the southern portion of the state. This is where we have transmission capacity. We have 2 345 lines, 45 kV lines from what used to be the Vermont Yankee substation to Cavendish. And there's not a lot of generation in this area of the state. So you can accommodate more solar PV or renewable energy in that part of the system. And as you go further north, you can see that the amount is reduced. Rutland can accommodate a fair amount, about 165 megawatts. The Scotney area, we call the Scotney area about 112. But as you go further north, you'll see that the amount is reduced. And within this year, but we know there's a constraint today, we're not adding any more solar PV in those pockets. So I realize the assumptions are optimistic, but if you do distribute solar PV in this way, from a transmission perspective alone, we can accommodate 1,000 or close to 1,000.
The caveat that this is transmission only is important because, of course, much of this resource is showing up on the distribution system, so the condition of the distribution system in southern Vermont may not be in a state that it can accommodate some of the assumptions we're making in the transmission level.
I guess when I say the assumptions are critical, one of the assumptions here is that larger scale resources do not connect. Right? So if we had 100 megawatts of a larger scale resource, the small scale resources we have to be reduced by that amount as well. We're importing power from New York through our PV20 line. So we import 150 megawatts from New York on that tie. That reduces the amount by 150 megawatts as well within the state. So it's critical.
I have a question about those little bars on the other chart, zonal hosting capacity. Are those, I assume those are megawatts?
Yes.
They would toggle according to what was happening elsewhere. For example, at the bottom of the green, the 225 to 250 megawatts. That range would depend on how much was built elsewhere in those other zones.
Yes.
And also, are those future, in other words, just want to confirm whether those are, you can accommodate that much more in each of those zones, or is that the total? Thank you.
And in this version, maybe I'm not understanding the table to the left, but you still show net megawatt loads in the losses column of the same 15 megawatts you're talking about. So I'm not sure why you say we could accommodate it. You mean we could accommodate it, but it would still cost a lot of money?
Yes.
Yes.
So if you wanted to make that net losses 0, does that mean no more solar?
Well, it's probably impossible. It's very difficult to actually reduce the losses, to eliminate all losses. Like, losses are sort of part of the system. Power has to flow. Anytime it flows on the network, it incurs losses. It's part of the physics. And the way to reduce losses is either to locate generation close to the load, and only as much as you need so that you do not increase flows on the transmission system. This case here, there's some areas where we're actually exceeding the amount of load in the area. For instance, Rutland has a gross load of 62 megawatts, but it can accommodate 100 megawatts more from a transmission perspective. There's enough transmission capacity to allow that to happen. But what happens is 100 megawatts of that has to flow elsewhere. It has to sort of serve load out of the Rutland area. So it's sort of, from a transmission capacity, it works, but it certainly is going to incur some losses to allow that to happen.
So just so I understand, so the 33.6 loss, that's already built into the system?
Yes.
That, you're losing that right now,
Right now.
just because load is not next to the source.
Correct.
And so it's the difference between 33.6 and 53.4 that you would lose if you use this scenario for the optimization based on transmission capability.
Correct, exactly. And that 53 is lower than we've seen in the past. So this was, say, a 20 megawatt delta in losses. So it's 20 megawatts in incremental losses because of 1,000 megawatt of solar PV, compared to what was, I think, 86 megawatts in the prior distribution. So by distributing solar PV in this way, you have lower losses than if you use the current distribution of solar PV. It's a better, and more spread out, better way of doing it.
I'm curious if you've had any reaction from the distribution utilities to sort of this map. I don't know in the context of the VSPC, or if there are discussions about it or anything like that. Have they said, oh, this is a problem for us, or we understand this, or have they reacted to it?
I think they understood the map. It wasn't characterized as a problem or not a problem. It's just that it's good information to have. They saw the problem distribution where you had transmission issues, subdivision problems, and all kinds of issues there. And there's a way to, this is as he's saying, there's a way to distribute solar PV to minimize system concerns. It's a good piece of information to have. Yeah, so it was appreciated.
Do they see it as a solution, like if you had some sort of statewide planning?
My view is you would have to have a much more coordinated, this is the first screen of how you might do a distribution of 1,000 megawatts. I think you need to do it through RDCs as they consider where they would want to see solar. You need to talk to the distribution utilities about what their systems can accommodate. Because of course down in southern Vermont you have a lot of places that are sparsely populated. You don't have a robust distribution system everywhere. So one of the screens is you'd want to bring it to the distribution utilities and have them say, okay, here's southern Vermont. It works great from a transmission perspective, but how does it work for your distribution network that you have in place?
Did you said RDCs, did you mean RPCs? Regional planning commissions?
Yes, the planning commissions. Because of course things like land use and other issues are going to come into play in a significant way.
So we've offered presentations to all the regional planning commissions in the state of the material that you're seeing here. And quite a number of them took us up on that because of their role in energy planning now. And actually, I think you'll see some information that we created for them, if I remember correctly, that is specifically answering some questions that were related to writing this down in the regional planning commissions. But one of the things that they really emphasized to us is the challenge of overlaying all of these different components, the distribution utility piece, the transmission piece, and their obligations in forming their regional energy plans. So that was a big takeaway for us is, yeah, we can present this piece of it. Our intention was to help developers, or one key intention is so that developers can see this picture of what's happening on the transmission system. But that piece of actually being able to see all the moving parts in some coordinated fashion was clearly an issue that we heard as we went around to the regional planning commissions.
Yeah. To the extent that the solar, and I know this isn't true by any means for all cases, but to the extent that the solar is right close to the load, the reason for the loss increase is that solar has now displaced some pre-existing source of energy, and that source of energy is now going to have to be shipped further because they've just lost a part of the load they were otherwise going to meet. Is that correct? Is that what's happening here?
I would just put it in a different way. That is, solar PV is incremental to generation that already exists. And that increment is in excess of the load that can consume that generation. The excess has to flow on the system to go to the next customer. The next customer could be within the boundaries of Vermont. It could be outside of Vermont. That's how we describe it.
Right, but if we think of solar as displacing, replacing, and we don't have this, but let's just assume that most of the generation in Vermont 20 years ago came from diesel fuel. Okay? Every time you put in a solar unit, you cause that diesel unit to not have to generate, that's a plus.
Sure.
What's happening now is we have a lot of renewable energy, and solar is coming in and technically, in some instances, displacing an already existent renewable energy, and that energy, the older energy, is now, if it's going to get dispatched, going to have to be dispatched over a longer distance.
Yes.
Great, Hans, can you just clarify your definition of loss on this study? It's not a displacement, is it? When you're talking about in any of the references previously to a loss on the system, it's a wasted megawatt.
Wasted, yes.
So it's being paid for by the system and being not consumed anywhere.
Correct.
Right, and I did understand that.
All right, thank you.
Ed, any question?
On the previous slide, so you have the net, at certain hours, it would be a net minus 440 megawatts. So if you talk to ISO New England, because that, to me, that means that Vermont is exporting 440 megawatts out of Vermont. So the system in Massachusetts and New Hampshire needs to be able to absorb that. And then the other question related to that is, when Vermont puts in when VELCO puts into the ISO system, here's what the load is in Vermont. You can't actually put a negative number, can you? And what's the impact there?
Right, you cannot. Although, what you could do is the load serving entities could register, and they could register two assets, and sort of register a generation asset and register a load asset. Right? So the load asset could go to 0 and the generation asset could go to 439. There's at least one utility in Vermont that has more generation than there's load. At certain hours where there would be injecting power into the system. From ISO's perspective, that would be sort of negative load, and it's not allowed. So the way they'd have to do this is when there's less generation than there's load, then this utility will look like a load to ISO, so it'll be positive, and that would be, as a load asset, you have a positive value. And when there's more generation than there's load, that load asset would be 0, and the generation asset will take over and will inject power into the system. So the utility would actually be two assets to make it work in the ISO model.
Okay, thanks. But have you talked with ISO about basically Vermont turning from, I think Tom said 80% of the time we're importing power to now we'd be exporting 439 megawatts?
We have provided the plan to ISO New England. Might have discussion with ISO on this issue. But they should be aware of the plan.
Thanks.
And the next slide is the same distribution, but represented by Regional Planning Commission. Again, this is for information for the commissions, but also to put this into context, right? We are testing 1,000 megawatt of solar PV. That may cause a lot of issues on the system, but when you compare it to the actual targets, about half of what is contemplated for 2050. it's less than what is contemplated from 2035, and it's just slightly above 728 megawatts, 2025. So it's 1,000 megawatt is not sort of out of the question. It appears large, but we put into perspective, it could be less than what is targeted by the regional planning commissions in total. And did some analysis after the fact, after the plan was published, and said, well, we had estimated the amount of storage as a non-transmission alternative. So it is another way of estimating this, and what we did here is that we compared the 2018 distribution against the optimized distribution. In some zones, you had the optimized distribution had more solar PV than the 2018, but in some areas it was less. For instance, in Newport, we had less solar PV than in 2018 distribution, so there's a delta. So, well, pick one of those. I picked the Highgate zone for an example, which shows that when you subtract the peaks here, this would be the capacity, the storage capacity that would be required in the Highgate zone for storage to address any kind of transmission issues. So 19 megawatts in this case would be required for capacity. When we think about battery storage, the capacity is one measure. We also need to know what the energy requirement of the battery is. So kind of how many hours of charging you actually need. And to do that, you have to calculate the area between this horizontal line and that top curve. You do a sort of an integral of the difference. But the way I did it here is I did the areas of the rectangles and the triangles, and what this is showing for Highgate is you need about 111 megawatt hours of battery storage energy, so that when you get to about 7 o'clock in the morning, the batteries start to charge, and they charge all the way down to about 7 o'clock at night, and then discharge for the rest of the day. That's a requirement for Highgate, for battery storage. And if you do that for all the areas where you had excess generation, then this is what this would look like for all the zones where the 2018 distribution was greater than the optimized distribution. So I have the energy requirement on the first row, the capacity requirement for the battery, and then what that would cost. And for this cost estimate, we used the paper that was published by Pacific Corp. Talked about the installed capacity, installed cost, the system cost, the kind of maintenance costs that go into that. It's just another kind of reference point for cost that can be considered. And I used, again, another lithium-ion technology, but the battery could be different technology. It could actually be a different storage device altogether. It could be pump hydro, it could be something else. So this is just again, just to give information of what that could be.
When you say the 2018 solar PV distribution, do you mean what's actually installed now?
So what's
or do you mean if you built it out, assuming the same distribution as in 2018?
The latter, yes. Compared to the optimized distribution, there's a difference. So the 2018 distribution caused a number of, in our analysis, showed some issues on the transmission system, transmission lines, voltage issues. You had an optimized scenario that would sort of mitigate that and minimize these problems, and there's a difference between those two distributions. And you could go forward with the 2018 distribution, but you need to use a battery technology to mitigate these problems, and this is what it would look like. And so I'm showing the capacity required for the battery as well as the amount of energy. You should be able to energy that would be able to absorb or charge, and that could be the install cost by area. So these are kind of generic costs. It's not for a specific device, but it would be generic cost. But it gives you a sense of what this would look like for a cost estimate.
So did you,
But the big picture.
did you compare, because you've given us several options. I mean, on slide a couple of slides ago, you have the maximum amount of solar PV that may be hosted with minimal system upgrades. That's where you distribute the solar into those areas that your transmission lines are best suited for.
Correct.
And here you're looking at, you're not changing that, you're simply saying if you put that much solar in that place, you need this much batteries. Have you compared what the relative costs are of those two different solutions, or whether if you put the two solutions together in some way, you get yet a different cost?
Well, what we did is we started the analysis using a distribution that is very similar to today's distribution. We call it 2018 distribution. And so you had a certain amount of transmission concerns associated with that. And then we've determined that there's a better way of distribution solar PV to avoid these concerns. And what we're saying here is that if we choose to continue the same path as of today, if we don't adopt the optimized distribution, we have to use batteries to compensate, to make the 2018 distribution work. And the storage capacity that you need would look like something like this, where you have just the capacity as well as the energy requirement for that. I did not estimate the solar PV cost associated with the optimized distribution. What I'm estimating is the battery option that will allow the 2018 distribution to work. Is that?
No, I understand.
So that's the energy storage that could be a solution if we choose to continue to develop storage, to develop solar PV in the same way. So that's the kind of the final analysis that we did. And this slide is a summary of the plan, stating that we'll continue to depend on transmission. We don't expect any load growth in the next 10 years. So there's no need to upgrade the transmission systems to serve peak load. There were some transmission issues that we flagged for the DUs to further evaluate. If we allow solar PV to grow in the same way as today, there may be some issues on the transmission system. It may require transmission upgrades, but only if we don't do certain things like adding storage to the system, load management. You can allow curtailment to some extent. Grid substation upgrades could have a role to play, but we can minimize that by doing storage and other measures. One key item as well that we're going to recommend is that the inverters that are installed have the ability to provide grid support. This is already in place as part of the IEEE 1547 standard, and the ISO New England source document is recommending that, and I think we're going forward with that. But that's really important to allow solar PV or wind inverters to provide grid support. And really doing this work, and this all solar PV analysis that we're doing is in addition to what the requirements of the planning process in Vermont. We think it's important for us to share the information with the Vermont planning community to allow us to make the right decision, to allow us to meet our goals.
So this information is necessary as other types of information, perhaps to know what the distribution capacities are, to know what land use issues are. This is just one layer that needs to be considered as we move forward with our 90% renewable energy goal per month.
How does a PV inverter or any inverter provide grid support? I'm not an engineer, so I realize I'm...
Right, so the inverter is a piece of electronic device that mimics what a generator would do. And the inverters today are able to provide both real power, so the megawatts that are usable. Well, the power electronics also provide reactive power, or power that a motor would need. So there's like two types of power that the system needs, real and reactive. The inverter can do that by power electronics that emulates a real generator. It's a device that connects to solar PV, that's for wind, or other devices that kind of connect the plant to the system. It's pretty interesting.
So how are those controlled then? Like, how would it know whether to be providing support to the grid?
So as any, so the inverter is kind of like a generator, right, electronic kind of thing. And there's sort of settings that you provide it. You can program into it that were at the substation that it connects to, it needs to, for example, hold 13.8 kV if that's where it connects to. So it's going to be 100% of the voltage. It will actually monitor that, and if the voltage tries to drift off of the 13.8 target, it'll push reactive power to support the voltage. If it's monitoring frequency, our system is a 60 Hz frequency. If there's an event on the system that causes the frequency to drift from the target frequency, the inverter is able to adjust its real power, maintain the frequency as close as possible to 60 Hz. So it's a control device, power electronics, and it's programmed to hold a particular value, whether it's voltage, frequency, or other parameters.
And are these only newer inverters that can do this, or can older inverters do it too?
Certainly, newer inverters are able to do that. Maybe the first inverters perhaps were not able to. The new inverters are called smart inverters, that are able to be programmed as controls and that allow these inverters to provide grid support. Older inverters, I don't know how far you can go, but perhaps they only do real power, no reactive power. Perhaps they do not do any frequency support, and they may even be forced to trip, meaning that they look at the system, they connect to the system. If they find that the voltage of the system is lower than they'd like, they will actually disconnect. They don't like what they see. So instead of providing support, they protect themselves. And it's not what we want. Older inverters work that way. And for some time it was okay. It was actually encouraged at some point for inverters to trip. But we wanted to get them out of the way so that we can repair the system and then come back. We find that there's so much renewable energy that's connecting, and it's actually displacing traditional generators that do provide that service, that we want the new inverters to provide the grid support that all more traditional generators used to provide. So the rules are changing, and they have changed. They have changed in California and Hawaii. The IEEE 1547 standards have changed. That will need to be implemented. I think it will probably be implemented next year at some point. The ISOs are putting rules in place for inverters to actually provide the grid support that they're able to provide. It's already programmed to do so. We have to enable that.
Do the utilities need software packages or upgrades to interact with these inverters, or the inverters do all this kind of on their own?
Inverters do that all on their own. So little knob, they're autonomous. They look at their system. Utilities can design the inverters to work together as a cohesive group. You have a number of inverters that connect to a feeder at multiple locations. You could have a control device at the substation that monitors what the inverter is doing and directing them to work together for the benefit of the grid. That also is possible.
Thank you.
That's all right.
Sorry. Some states are encouraging electric vehicle charging during PV peak output times instead of at night as a way to address the excess PV power that's being dumped into the system. I'm wondering to what extent have you considered that in your modeling assumptions and calculations?
We have not specifically. We're using the example of storage here, lithium-ion battery storage as a solution. Part of that could be from electric vehicles. I mean, the battery doesn't have to be located at a substation. It could be the battery from an electric vehicle. When it's connected to the system and it's charging, well, it does the same thing. Right? It absorbs the power that would have flown on the system. Fluid management could be considered as storage to some extent, right? You can have a water heater that absorbs that energy in the middle of the day, and it can be controlled by the utility. That is some form of storage. I think today, currently, it's the distribution system that's the battery storage for excess energy. Energy goes elsewhere. It serves load elsewhere. And when the solar PV is shut down, well, other states serve this thing. So it's kind of back and forth like that. So yeah, so I did not look at the electric vehicles specifically, but it's kind of the same concept, right?
Are there any other questions on the plan? Yes, ma'am.
Could you remind me your name again, please?
Oh, first name is Ariel, last name is Arwen. Commissioner Roisman mentioned that Green Mountain Power has been discussing efforts to increase microgrids, and I wondered if you could speak a little bit about how your work, even though that's not quite here so much yet, and you said this didn't address it all that much, if you could address how you see that issue?
So microgrids are a way to serve a local area load by existing resources, a combination of renewable energy, could be batteries, solar PV, actually gas turbines or anything like that. So it's a local area, it could be a community, it could be a factory that serves its own load. So the microgrid, when it exists, it reduces the load that the system would need to serve. So it would be a reduction in our load forecast, for instance, so that the system is not required to serve that load. If it's autonomous, it can serve its own energy, and it is load that the system does not need to serve. And if there's growth in smart grid systems, whether it's GMP or Global Foundries or OMIA or other projects, then our load will be reduced by that amount, and we'll take that into consideration. So we'll need to follow that and pay attention to what's happening in the industry within Vermont.
So does that increase this loss issue quite a bit?
It may. If there's more excess power, and if you have microgrids and solar PV, so it's not, you have both, then you're gonna have more generation, more excess generation that needs to flow in the system. So that could increase losses, yes, it's possible.
This is a really naive question because I'm pretty much a big layman, but how do we get more distributed energy and keep the utilities in business then?
That's an excellent question. We have the answer to that. It's, somebody wants to answer that. I don't have to that question. It's a difficult one. Certainly a difficult one, yes.
Are there any other questions?
Just to say thank you again to the Commission for hosting us today, and I hope this was an informative day. I recognize that you know, some of the areas, storage and some solutions, we don't have all of the answers. We've put some information out there about the size, but as I've observed, you know, running the grid is becoming more complex than it used to be. There used to be 300 generators in New England, and now there are thousands and thousands of generators. There's more uncertainty about things like demand and how fast are things like solar going to happen. We have energy policy that's getting us to 90% renewable by 2050. One question that's not answered here is how much of that 90% comes from Vermont-sourced projects. I hope that this informs the perspective, at least, that it just provides a perspective that there are some challenges with putting more resources here in Vermont. On the plus side, I think there are opportunities today that didn't exist even 5 years ago. Storage is an ideal resource in terms of it being both a flexible demand and, of course, a means to supply power at times when the solar is not available. Today, or at least in our most recent information, looking at 2017, it's in the appendices, you know, Vermont was importing power 100% of the time. That was the physical flows. Will that change as we put more and more resources and we put in more storage? I think probably the answer is probably yes. But I think what's very clear from the work that we've done and some of the information we've produced is additional coordination among the various parties that are coming to the table. We have the transmission perspective. Obviously, the distribution utilities have a key role in all of this, as do other parties who are part of this conversation. And we have that discussion today at the Vermont System Planning Commission. That I think there's always an opportunity to improve the amount of coordination that takes place today. And certainly we're going to be part of that conversation and playing a constructive role as much as possible so we can advance the state's policies.